first part, but now I'm recording.
Redman.
Dropping the ball.
He's too busy.
So we're identifying the snapshot values. That's to say the values of the variables and or the rates of change that were given in the problem at that particular moment, at the particular moment in question. So for us, the moment in question is the moment when the radius is 10 feet. That identifies the specific frame in the video that we're interested in. Out of all the infinite frames, that's the one we're interested in. Okay. It's often helpful to make a sketch. And this is important. This is going to be, calculus becomes, you draw lots of pictures and graphs and diagrams of calculus. And this is a case where we're doing problems like this where it's really critical to draw pictures. So when you're drawing your picture, and we'll go through all this stuff in several examples, over the next few days, we're just going to do examples of this. We make a sketch and label all the variables. So anything that's changing, we're going to label as a variable, and we'll identify what the variables are. If there are constants, we want to add those as numbers, so we can see right away in our picture that those are things that don't change. Anything that shows up as a number is something that's static. Anything that shows up as a variable can vary, it can change. Okay? So let's do that first. This is a pretty simple one, right? In this case, arguably you could even maybe skip the picture because it's so simple, but we'll do it. We'll cheat here. So here's our sphere. Okay, so what do we know? What are the variables in this case? Only one that we can draw. Radius. Okay, so we get the radius. So the radius we'll call R. Okay. And we want to label all of our snapshot values. Okay, so at this moment in time when the radius is 10 feet, well, let's put that, right? So this is step one. So one of them is R equals 10 feet. Agreed? Okay, what else? What else are we given here? So you're kind of looking for numbers. Okay, what about that? 400 is there's a number. What is that? Rate of change of what? Volume. Yeah, okay. It's the rate of change of volume. And how do we know, and I know this might seem, it might seem like overkill, but I want to point this out. Well, how do we see immediately that that's a rate?
It says a rate.
Okay, but what if I didn't say a rate? I didn't have to. I could have said gas is being forced into a balloon at 400 cubic feet per minute.
For the amount of time.
Okay, yeah, look, when I say that, I had to use the word per, right? So you look at the units. Dimensional analysis ends up being really beneficial to us in science, but also in math. We're doing applications of math. We want to look at the units. Now, we know that because it tells us this is the radius, but even just the 10 feet part, the feet is telling us, okay, this is a linear measure, right? This is a distance. Up here, this is in cubic feet per minute, so we have to ask ourselves, okay, now what is that a rate of? And look at the units. Cubic feet is a rate of volume, and feet, or minutes in this case, is a rate of time. So that's the rate of change of volume with respect to time. Agreed? That sounds like a derivative, right? Rates of change are derivatives. And so how would I say that as a derivative? D what? D what? dV, right? Right? I've got dV because, look, I've got units of volume divided by units of time. Okay, good. So I've got units of volume over units of time. Like that? Everybody agree? we're gonna deal with lots of rates and related rates problems. And this is, when you move forward in calculus, you'll go through your calculus series, and then you're gonna move into differential equations, assuming, I'm sure you're all gonna continue on with math for a long, long time. Into math, or into differential equations classes, and then partial differential equations. And they all deal with stuff like this. They're all dealing with solving equations that involve derivatives, right? And derivatives are cumbersome to write. And visually, we don't want our math to look really busy on the page. We want it to look easier to follow. And so we do something here. Not all books do this, but my background's in physics, and this is huge in physics. Be prepared to see this, and we'll do it this year. Anytime you're dealing with an application like this where you're differentiating something with respect to time, normally we'd call that a v prime, right? We abbreviate our derivatives as primes. Well, what do you think a dot means? It's a specific kind of prime. When I'm differentiating with respect to time, yeah. Anytime I'm differentiating something with respect to time, which is almost always what I do in an application, right? You want to know how some system is evolving in time, I'm going to use a dot instead. So v dot from now on is going to mean dv dt, right? So what is v dot? 400. And if I want to include the minutes, cubic feet per minute, okay? Let's talk about units for just a second. So in physics, a lot of times we'll talk about suppressing the units, which is just really shorthand for allowing ourselves to be a little bit lazy and not have to write those units the whole time. You can do that. You can ignore the units when you're doing your calculations as long as the units all fit together, right? So if I had, for example, cubic feet per minute here, and I wanted to know the rate at which the radius is growing in feet per second, then I could no longer suppress the units because I've got minutes here and seconds there, right? Once I get all the units agreeing, so the distances or the lengths are being measured in feet, the time is being measured in minutes, for example, from that point forward, I could probably just, I can just get rid of the units, and when I'm all done, what are the units of my answer going to be? R dot would be measured in what? Rate of change of radius would be feet per minute, right? And then I just know that my answer has to be in those units, and I don't have to write the units every time. That makes sense? I mean, these are just minor points, but things worth mentioning. So that's the stuff that we're given. What are we trying to find? That's the other thing that we want to write down here. Okay, so we want to find our dot, right? So there it is. These are the three quantities that we're given and or trying to find. This is the simple picture that's going to relate those quantities, okay? So next step, right? There's everything that we're given, what we're trying to find. The next step is to create a parent equation involving all the variables included in the snapshot values and all the variables whose rates are included in the snapshot values. Whenever possible, the parent equation should end up being a function of a single independent variable. We'll get to that. Okay. So in this case, we can sort of blur our calculus vision here and just ignore the dots. What are the static quantities that we're relating here? If I ignore the dots, we're relating what variables? But variables here. So I don't want numbers, I want variables. V and R, yeah, volume and radius. Everybody agree? Okay, so the static equation we're going to get then is just going to be the volume equation, which is given to us right there. Okay, so step 2, I'm just going to kind of partition this off here. I'm probably going to run out of room, but I can make more, I guess. So step 2 is parent equation. That's just going to be V equals 4/3 pi r cubed. Okay, now we get to calculus. What do you think the next step's going to be? Yeah, right. Here's where we're going to differentiate with respect to, say it again? Well, I'm going to differentiate all this stuff, but when I take a derivative, I have to differentiate with respect to something. With respect to t, right? I'm going to implicitly differentiate with respect to t, and think why that is. When all the dust settles, if I differentiate with respect to t, what am I going to end up with on the left side? dV dt, so a v dot, right? On the right side, by the chain rule, I'm gonna get, I'm gonna get some r's, but I'm also gonna be guaranteed to get an r dot, right? When I differentiate r cubed with respect to t, I'm gonna get a 3r squared times the r dt, so an r dot, right? So that's what's gonna link together these rates that we started off with, right? So step 3 then is always gonna be use the chain rule to implicitly differentiate with respect to t. So let's do that. What do I get if I differentiate this? On the left side I get v dot, so here's step 3. V dot, what about over here? I'm gonna get 4/3 pi, that's a constant. What's the derivative of r cubed with respect to t? 3r squared times r dot. Well, the 3 and the 1/3 cancel, and I get 4 pi r squared r dot. Everybody agree? Okay. And then finally, we're done. Now the last step is just plug and chug. Right now, all we have to do is solve for the variable that we're trying to find, and then plug and chug. So in here, we're trying to solve for r dot. So to isolate r dot, I would just divide each side by 4 pi r squared. So we get r dot equals v dot over 4 pi r squared. And if I plug in values from my snapshot menu up here then, that just gives me 400, and the units, I'm going to draw these in lightly, but you'll see once again that we don't even have to, right? We just know the answer's got to be in feet per minute. And then what do we get here, 10? And what's that going to give us when I do that math? 10 squared is? So I get 400 divided by 400 pi is just 1 over pi. And look, I'm going to get cubic feet per minute divided by square feet. We have to square the units, right? Which sure enough gives us our appropriate units, feet per minute. Right? Get the idea?
Yeah.
Okay. And so then, one other point I'll make about that. Whoops. So the snapshot values, there's a real tendency here when people are first doing this, they want to plug stuff in. Notice that we can't plug in the snapshot values of the variables until after we've differentiated. How come? Like what would have happened here if I had tried to plug in, the 10 for the radius on this side first? Before I differentiated, I would have gotten v equals some number on this side.
You wouldn't end up with R
Yeah, I wouldn't get an r dot, would I? In fact, when I differentiate, if I plugged in 10 for r here, I would have just gotten v equals some number. And what's the derivative of a constant? Derivative of a number? 0. So the derivative wouldn't have worked, right? You can't plug in until after you differentiate. And we'll see the same thing when we do optimization here. So you can't ever plug in those values until after you take the derivatives. Okay, so what about part 2 then? At what rate is the surface area growing when the radius is 10 feet? Well, this is really just a separate question, but we can just tack this on to the work that we did up here, right? So what is that asking us now? We've got all the same snapshot values. We could even fill in the blanks here for r dot. We know we now know that it's 1 over pi. What's the only additional thing we're trying to find in part 2?
Surface area.
Yeah, surface area. Good. So we would just have S dot equals whatever, right? So there's step 1. What's step 2?
The parent
Parent equation. Good. So we got our parent equation. Now is just going to be the, did I give it to us? Yeah, surface area equation. S equals 4 pi r squared. Now what? Differentiate implicitly with respect to t. So what are we going to get on the left side?
S
Okay, over here. R dot. Okay, and this is already, we're trying to find S dot, the rate at which the surface area is growing. And so now we don't have to do any algebra, we just plug and chug. So I end up with S dot equals 8 pi times, radius was 10, right? And R dot was 1 over pi. I'm not going to worry about the units because we know the units all match. So look, the pi's cancel, and I just get 80. What should my units be for S dot, rate of change of surface area?
Feet squared.
There it is. Okay, get the idea? Okay, let's try another one. What about this one? It really pays at this point, when you start getting this far along in math, I mean, in physics and any kind of analytical stuff, you really want to just, don't jump into something before you've had a chance to digest it. Read it a few times, pause and think about it. I know you're driven students, you want to get this stuff over with and get it done, but you'll save yourself a lot of wasted time if you just slow down for a second. Think about, what am I trying to do here? So can anybody articulate, what is it that this is, what is this problem asking?
What's the rate of the light? What's the difference in that?
And the rate of change of the distance between the origin and the moving point. Can you think of like, what's a way, and I think this is a useful skill. Can you think of a way, like what if you were trying to explain this problem to somebody who were in some class below the level of calculus? You wanted them to be able to visualize what's going on. How could you do that?
Trying to figure out, if you're the origin, trying to figure out how fast something can move.
Yeah, okay, so like if you were, like if you had some kind of a, you could measure the distance via GPS or something, and somebody's driving along on this parabolic trajectory, right? You want to know how fast is your distance changing between, does that make sense? Or maybe like if you bend a wire in the shape of this parabola, and you slide a bead along that wire, if you know that the bead, what's dx dt?
X dot.
That's x dot. What does that mean though? In the context of like, I'm gonna graph this thing really quick, just so we have something to look at.
It's just
Changing-
where the
changing
dot
the
is.
X along the top.
Ah, okay. Right, so this is a simple parabola, right? It's just been vertically
Yeah.
translated by one, right? So we get something like this. Something like that, right? We've got this bead that's sliding around on the parabola. So dx dt, that's, now if you're in physics, this is gonna be a little easier to handle probably because you've talked about components. Isn't that really just the x component of velocity, right? The rate of change of the x. That would be like if you were up above staring down on this thing. That would be how fast you see that bead moving horizontally, right? So if you took that perspective, if you took the perspective up here looking down, you would be sort of isolating the x component of velocity, and that would be the x dt. Dy dt would be if I'm looking from over here, and so I can't judge how close or far it is from you horizontally, but vertically I can see that bead moving, right? You get the idea? Okay. All right, so there's our picture. What are we gonna do here? Let's go through the steps. What's step one?
Yeah, I don't make this snapshot.
Okay, snapshot values. Okay, well, there's only one value that's given to us.
No, X dot is two.
There you go. So we know x dot is 2. So step one, x dot equals 2. What are we trying to find?
Y dot.
Not exactly. Okay, we need another, we need to maybe change our picture just a little bit. Here's the origin, right? And here's a point with coordinates. What are the coordinates of the point? Well, okay, we don't know for sure,
Slightly.
but what variables could we introduce? X and Y, there we go. X and Y, right? So X and Y are just the normal variables, right? And what we're really looking for here is that, aren't we? The rate of change of that quantity. What are we gonna call that? Distance, right?
Yeah.
Let's call it S. And there in our picture, that's defining that distance, okay? In terms of S, aren't we just trying to find S dot? Okay? All right. So right away, what's the problem that we see here? Okay, we don't know X or Y, and we don't have any information about Y at all, do we? Right? So if we were just to plow ahead with this, step 2, where we come up with our parent equation, I want you to really think about this. Step 2 would have to be the relationship between S, which is what we're trying to find, and X dot, which is what we're given, right? Without the dots, right? We want to eliminate the dots and just think of a static equation. Well, what would the equation be there? What's going to relate S to X and Y? Yeah, you just use, the distance formula really is just Pythagorean theorem, isn't it?
Yeah.
Just Pythagorean triangle, just a right triangle. So we've got something like, as I've drawn it there, we've got a right triangle, right? And this is going to be X, and that's Y. And so we just get S squared equals X squared plus Y squared. Okay, everybody with me?
Yeah.
Okay? Okay, that seems fine, right?
Yeah.
I could differentiate that. Now, if I were to differentiate that, I'm gonna get 2S, S dot, agreed,
Yeah.
equals 2X, X dot, plus 2Y, Y dot. And I could even divide both sides by 2 if I wanted to, right? And I've got S, S dot, equals X, X dot, plus Y, Y dot. Now the problem has become more obvious. When I want to plug and chug, I want to solve for S dot and plug and chug. What's the problem?
You only have X.
Yeah, all I've got in there is X dot, right? So I inherited some difficulties when I included that Y. Can we bail ourselves out?
We have the definition of Y and things
Okay, let me see this. Look right here. Does everybody see that? Okay, this is what we could call a secondary equation. We have some other equation that relates the independent variables, right? The variables that we're inputting to find S, the X and the Y. Look, we have this other equation that relates those two, okay? Now, why wouldn't we? This is a lot smarter to do it this way, isn't it? We could plug in the value of Y down there immediately, and what do I get? Well, I mean, I'm gonna get only X's in my answer,
Yeah.
right? So if I plug that in, I'm gonna get S squared equals X squared plus Y, which is the quantity X squared plus 1 squared. Way better, right? Way better. If I simplify that, what am I gonna get? X to the 4th plus 2x squared plus 1 plus another x squared, right? Plus 3x squared plus 1. Everybody see what I did? I'm
Yeah.
just expanding out, a plus b squared is a squared plus 2ab plus b squared. Okay? Now that's a little better. Now when I differentiate, it looks much better. I'm only getting 2s s dot, so we're just going to do away with all that stuff, right? Equals 4x cubed x dot plus 3x squared, whoops, 3x sorry, 6x, what am I doing? I'll bring that 2 down, right? And get 6x, x dot. And I could even factor an x dot out if I wanted to, right? So now I've only got, it still isn't perfect. I've still got s's and x's and all that stuff in there, but at least I don't have those y's, okay? Could we, okay, so could we, if I wanted to get an answer here for s dot, I could divide everything by 2, right?
Yeah.
Factor out an x dot, pause there, does that make sense? Get it? One other little issue. When I solve for s dot, I'm gonna have to divide each side by s. How do I deal with that? I don't have an s in my snapshot values up here. Right. I could instead, I could write that s in terms of x's though,
Yeah.
right? Everybody see that? Because look, I've got s squared defined up here. So I could, instead of writing this as s dot equals 2x cubed plus 3x, x dot divided by s, I could instead write that with x's as the square root of x to the 4th plus 3x squared plus 1. I am ultimately stuck though, aren't I? Right? I'm not gonna, I don't have enough information to plug in. And so this really is, it's not a bogus problem, but it's a bogus problem in the sense that I can't get a specific answer. How come?
You don't have enough information.
I don't have enough information. What else would I need? And I'd need an x, wouldn't I? Because the answer is gonna depend on x. How can we guarantee that the answer is gonna depend on x? The math gods told us it did, right? When we calculated s dot, the math gods told us that this is the answer, which depends on x dots and x's, right? So because we got x's in our answer, it is, we know right away that, and this really helps you improve your intuition about problems. You know, now you know, okay, this is definitely gonna have some association with x. Initially, you may, I mean, you could have thought about it and probably convinced yourself of that, but initially you might have thought, maybe this is gonna be independent of x, and it's gonna be the same answer regardless. Sometimes that happens, but in this case it didn't, right? I would need to be able to plug in values of x also, okay? And so all we could do, the very best we could do here, is we could plug in 2 for x dot, and then we would get s dot equals 2 times all this stuff in terms of x. And then we'd have to still feed it a value of x to get an answer. Okay? Make sense? Okay? All right. When are we out of here? 25? Okay, that's a good place to stop. I'm gonna break this aside. Here's my plan on this. I wanna break this up into some parts. Like, I don't wanna just give you one, because these problems, as you can guess, these problems each take a little while to do, right? I mean, it's a process problem instead of just getting, taking a derivative and getting an answer. So I'm gonna give you like shorter assignments so we can kind of keep on pace. Because what I wanna be able to do with this is I wanna be able to say, okay, I'd like you guys to do these problems initially. There's sort of a progression through these kinds of problems. I want you to do sort of the level 1 problems and then we'll go into some level 2 problems and so on, right? I'm gonna start off giving you a couple, I'll give you a combination also of some Math Excel problems. I think those are useful. I'm sure you guys like those a little bit because you can go to the, help me
Yeah.
solve this thing, right? But I also want to give you a couple of these for their paper and pencil, right? Where I can see the process, you can write down the steps. We're starting to get to that part of the calculus class, right? I want to make sure that you're organizing your thinking on this in an appropriate way. So there'll probably be a total of like, I don't know, 4 assignments on this. Each one of them only being a couple problems, okay? That make sense?
Yeah.
Okay.